Welcome to differentiation and continuity. Right? So we'll just start off with a nice little comic strip here, a little cartoon. How's my deriving? Call 1-800-555-MATH. Can't resist a good calculus pun. And if we look carefully at his work, he is doing the limit of the difference quotient, which means he's finding the derivative. So a little review of the derivative, quick little review till we get, and then we'll get into our concept for today. Using limits to calculate the derivative. So the derivative of f of x at the point a, f of a, is f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a divided by h. So as these 2 points, a and h, are getting so close together that the distance between them is approaching 0, so there's no distance at all, when we take that limit, we get the slope of the tangent line, the derivative, the instantaneous rate of change. So the derivative function, or just the derivative, is a function that can provide the slope of the tangent line for a given x value. Right? And another way to think of it, it's the instantaneous rate of change. It's also the slope of the tangent line. Let's add that too. Just as a little reminder, it's a good thing to review. Just lost my E. Slope of the tangent line. All these things are one and the same. And you already have that in your notes. You don't have this graph, but I'm going to go over it with you. I had to darken it because it was a little too light. And we actually have two functions graphed here. We have y equals f of x, and we have y equals f prime of x. So we have the function, and we have its derivative. And while you don't need to copy the graph down, although you certainly can, you have a blank page right next to this in your book, you might want to write down some key ideas, and I'll kind of guide you to those key ideas. All right, so we're taking a look at our green function here, and I wish I had a way to point to things. You know, if I had a little arrow, for instance, I would have a way to point to things. And I can get a little arrow because I think hidden under here is an arrow. There we go. I think I want a skinnier arrow. Oops, not that skinny. Not that fat. There we go. Good enough. And I'm going to just turn this around a little bit. There we go. Now I've got a way to point. Because you can't see my finger pointing. Oops. Now, do you? If you look up there, I see the box here that says, I no longer have a shape tool out. But for some reason, it wants to make me a shape. And for some reason, it wants to make me a circle. And I really did not need a circle. How about now? Actually, I'm going to pick up a pen. Maybe that will make sure that I do not have a shape tool out. There we go. All right, so here's our function. All right, and so we're increasing at a constant rate here. Got a diagonal line. And notice the derivative that goes with it. All right, it is horizontal. All right, it's a positive value. All right, so f prime of x here is positive. It's above the x-axis, right? These are all my positive values. Down here are all the negative values. All right, so we have positive f prime of x because the function is increasing. All right, so that might be something to write down. All right, so we're keep on increasing here, and then right, we change, still increasing. But notice that it's not so steep anymore. All right, this was a much steeper line than this was. All right, so we have a smaller slope here, and so notice we have a smaller value for our derivative. Right? Because the slope's not as steep. And all of these y values represent the slopes of the tangent lines. Now, something I want to point out too, do you notice here, there is a hole. There's a gap. First of all, there's a big jump discontinuity here, and there's a hole. Look, there's no point here. There's no point here. I'm just missing this whole value from my derivative. Notice if I keep going up, look what's on my function. So Just kind of, store that away in your head. All right, so let's follow the function again. All of these, by the way, are constant rates of change. They're a bunch of lines. So this is a piecewise function, a bunch of linear functions all put together. All right, so this is a really not very steep slope at all. It's still increasing, but just not as much. So our value of our derivative is even less. But it's a horizontal, it's a line, excuse me, it's not a horizontal line, it's a line. It's a diagonal line, oblique line. And so we have a constant rate of change here. It's just not, as the y value is smaller than it was over here and over here, because the slope is not as steep. All right, so now we get here. Oh, and by the way, notice this. I got a gap here. I got a gap, and that value doesn't exist. And over here, here's my function. If I go straight down, I have a gap, and it doesn't exist. That value just doesn't exist. Wonder why? I wonder why I have all these gaps. All right, so there's no gaps in the function. This is a continuous function. So now I have a negative slope. So we're decreasing at a constant rate. So again, my derivative is a straight horizontal line because I have a constant rate, whatever this value happens to be, because there's no y values on this on the coordinate plane here. And notice it's below the x-axis. Right? So our derivative is negative. We have negative values for our derivative because we have a negative slope. Right? All right, so I'm going to put my arrow away for a moment. Well, actually, I'm going to point out a couple things. All right, so we have a negative derivative because the function's decreasing. And as a reminder, the derivative is just the slope of the function, f of x. All right, just a bunch of slopes, just all graphed together. Right? And some places where our derivative does not exist. So all these open holes, our derivative just doesn't exist. I put my arrow away now. All right, so the derivative is defined at the endpoints of a function on a closed interval. So the derivative, oh, come on, arrow. Whoop, there you go. The derivative does exist here at the endpoint. It does exist here at this endpoint, but it does not exist here, here, and here. Any thoughts to why? Well, I am going to go over it. All right, so continuity in the derivative. Since the derivative is a limit as h approaches 0, and since the point of tangency must be on the curve, a function does not have a derivative where it is not continuous. But notice this is a continuous function. There's no problems with continuity on this particular function, but notice there are places where the derivative just does not exist. All right, so, but if you're not continuous, you will have places where your derivative does not exist. So in other words, so a function, let's go back to that sentence again. A function does not have a derivative where it's not continuous. In other words, if a function is differentiable at x equals c, then the function must be continuous at x equals c. Differentiability implies continuity. So if you are differentiable everywhere, you are absolutely continuous. Right? But this function was continuous, but not differentiable everywhere. So we can see, I think, from this diagram, from that graph, that this is not a two-way street. So although differentiability always implies continuity, you will only be differentiable at all the places on a closed interval, at every point at that closed interval, if you're a continuous function. But it does not work the other way. So if a function is differentiable, it has a derivative at a point or over an interval, then it is continuous at that point or on that interval. Right? And we can have functions that are differentiable everywhere, and that means they are continuous everywhere. Right? So differentiability implies continuity. So if you're asked if a function is continuous and you are told it's differentiable, you can know for sure that it is continuous because differentiability implies continuity. Very important concept. That's why I put a big old asterisk next to it. And I think you have the big old asterisk in your notes as well. All right, so this is a key concept. So this is a short lesson, but it's got some key concepts. Let's look at that statement the other direction. Important note, although all differentiable functions are continuous, not all continuous functions are differentiable. This means it only works one direction. Right? Like the band, one direction. This only works one direction. If a function is differentiable, it's continuous. But if the function is continuous, it's not necessarily differentiable. So differentiability implies continuity, but continuity does not imply differentiability. Right? You might have noticed some features of this graph, and maybe you have figured out without me even telling you what the problem for this graph might be. So you can check yourself, because I'm going to go over what makes a continuous function not differentiable. Let's get to that page. Oh, it's on the next page, but I'm going to read this part, then I'm going to get to that. So a function is differentiable if it has a derivative everywhere in its domain. It must be continuous and smooth. Functions on closed intervals must have one-sided derivatives defined at the endpoints. Right? So if your endpoint is a closed point, not an open point, then you are differentiable at that endpoint, and it's a one-sided derivative. All right? But notice that these words that were underlined: continuous and smooth. Was our graph? It was continuous, but was our graph smooth? No, it was not. To be differentiable, a function must be continuous and smooth. Derivatives will fail to exist. In other words, they will not exist at corners. Right? So that's what we had here. Our piecewise function with all those little linear pieces was loaded with corners. It had, come on little graph, there you are. Come on little arrow. Oop, here it comes. We had a corner right here, so it was not differentiable there. We had a corner right here, not differentiable. And a corner over here, not differentiable. So everywhere this graph has a corner, this graph was, let me move this arrow away. This graph was not differentiable. All right, let's go through the other ones. Cusps. All right, so a cusp is an awful lot like a corner, except a cusp is curved. Think of like a peak on a wave, or if you're frosting a cake and you make little peaks, right? Those are cusps, right? Not differentiable at that cusp. Vertical tangent lines. So here, cube root of x, we have a very steep curve there. How would I draw that tangent line in? It would end up being a vertical line. So that is not differentiable at that point. And if you're discontinuous, if you have a discontinuity, the function will not be differentiable at that discontinuity. Now, this does not mean that these functions aren't differentiable other places. It's just at the corners, the cusps, where there's vertical tangents or where there's discontinuities. These are the 4 reasons that a function would not be differentiable. Okay? So then you do need to know those. All right? But I bet you had figured out the corner. So if f has a derivative at x equals a, then f is continuous at x equals a. Since a function must be continuous to have a derivative, if it has a derivative, then it is continuous. Let's put a star next to that. This would be a great reason on an FRQ to state that a function is continuous if you're told that it's differentiable. A lot of times in a question, it might say, in a FRQ, it might say a twice differentiable function, blah blah blah, and they just tiny little word in there. If you catch that, hey, it's a differentiable function, then you know it has to be continuous. So you can use this as a reason for continuity. Sometimes students miss that. Now, I don't want you to miss that. And we're going to just take a tiny little look at the intermediate value theorem for derivatives. And intermediate value theorem for derivatives is really just like intermediate value theorem for other functions as well, because a derivative is just a function. So if you remember intermediate value, that if you have a function that's continuous on a closed interval, and you have some y value that's between the y value for some point, right? You have to have every single y value between those, right? So there's some c for that y value such that f of c is equal to that y value. All right, let's go. I'm going to go through that one more time, and maybe in better words. If a and b are any 2 points on an interval of which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. Right? So here we have, and this is in your notes, we have a graph. And f prime of a, excuse me, this is the graph of the derivative, is 1/2, and f prime of b is 3. That means that there is some x value oh, come on. And we'll call that x value c because we like that one. Such that f of c equals k according to IVD, our intermediate value theorem, and this is for derivatives. Now, importantly, it has to meet our one key requirement, and that is, and actually I'm going to put it at the end there, provided that f prime of x is continuous. I think I just wrote all over my graph. All right, so this works just like intermediate value theorem for any function. All right, it's just for derivatives because this is the derivative function. But a derivative is just a function. Just a function that gives us the slopes of the tangent lines. I'm going to move that up just a little bit. All right, so I'm not going to, we spent a lot of time on intermediate value theorem when we were dealing with just for functions, so I'm not going to spend a whole lot of time with derivatives because it's the exact same thing. And this is where I'm going to take a pause. All right, and looks like I'm just kind of noticing that you have some things I had erased on my slide that are in your notes. So I'm just going to add them very quickly. All right, so I'm just going to add this as well. I kind of have it up there, but I'll put this in your notes, put it down here in these notes as well. There is some x value between, oh, that looks terrible. A and B. See if I can squeeze this in. I have it on the other side on your notes. For every y value between f of a and f of b. I'm writing faster than it's showing up, so I can't tell what it looks like. I'll take it. It's not that bad. I'm just going to move that over a little bit. Okay? And when you, just a little hint, when you're justifying intermediate value theorem, always take a look back and make sure you said everything. There was one little thing I didn't put in that. Oops, come on. Between A and B. Right? It doesn't apply if our x value is outside the interval of a and b. So let's just add that in there. All right? And that's all I'm going to say right now on intermediate value theorem for derivatives. I think that's my clue to end this video. So in the next sequence of videos, and I say sequence because it's going to have some audience participation. Right? So there's going to be a little mini quiz that comes up with like one question, this one. And so you're going to answer given our graph, and then in the next video I'll go over it. All right? So the next thing you'll see is this question in a little mini quiz, and then the next time you hear me, I'll be going over the answer so you can see how you did. All right? Bye for now. Thanks for watching.